Then question number 13. So I will draw the diagram so that this is the diagram given. Here one section is there, transmission line section. For this load impedance is 100 ohm, characteristic impedance is 50 ohm, and this length of this transmission line is lambda by 4. Okay. Now another section is there here. Okay. So this section 200 ohm. Once again, the length of this is lambda by 4 only. For this section, characteristic impedance is equal to once again 50 ohm. First section lambda by 4, second section means length actually. So the length of this transmission line is lambda by 4, the length of this is lambda by 4. Now these two sections are in parallel, and there is a third transmission line, the length of this is also lambda by 4, like this it is given, and the characteristic impedance of this is also 50 ohm only. Now what is reflection coefficient at the input? That is the meaning. Okay. So you find this is the first transmission line. I will take ZL1. I will take this as a ZL1 is 100. I will take this as second section ZL2 200. So input impedance of this first section Zn1, I am taking this as a first transmission line. This is lambda by 4 line. For lambda by 4 line, so it is Z0 square by ZL1. That is nothing but 50 square divided by 100. So am I right? 50 square by 100. So that is 50 into 50 divided by 100. So you get 25 ohm, that is. So am I correct? 50, 2 zeros gone, 5 into 5, 25. Now what is the input impedance of this second transmission line? The characteristic impedance of this is 50. This is once again lambda by 4. That is why I am taking like that formula. We have to use input impedance of lambda by 4 transmission line is equal to Z0 square by ZL. So the input impedance of this is 50 square divided by ZL is 200. That is 50 into 50 divided by 200. So ultimately you get cancel. So 25 divided by 2 ohm you get. Now the input impedance of these two sections behaves like a load impedance to this third transmission line. ZL3 load impedance to this third transmission line is equal to Zn1 parallel combination of Zn2, this one. So that is nothing but 25 parallel combination of 25 by 2, that is 25 by 3 you get. So Zn1 parallel combination 25 parallel combination of 25 by 2, 25 by 3 you get. That means the load impedance of this section is input impedance of these two sections. Now what is the input impedance of this lambda by 4 section? The characteristic impedance is Z0, so that is Z0 square divided by ZL3, that is 50 square divided by ZL3 is 25 by 3. So ultimately that Zin is equal to how much you got, students? 50 into 50 divided by 25. 5 gone, 100. So you get 300, students. By 3 is there, multiplied 300 ohm you get. Now discussion is like this. ऐसा रहता है discussion. One transmission line characteristic impedance Z0, then this is ZL. If you want reflection coefficient at load, what you do? This side impedance is this side load impedance is ZL minus of this side transmission line should be there. That transmission line characteristic impedance is Z0 divided by same thing you write and put the plus sign. So here you want reflection coefficient. Then assume that one transmission line is there here. Assume that one transmission line is there here. Like this. One transmission line is there. Assume that one transmission line is there this side also. How much length? Tends to 0 length. Very small length transmission line is there, you assume. Very small length. How much length? Tends to 0. Then that transmission line characteristic impedance is also Z0, you take same. So dear students, that is the procedure actually. You want a reflection coefficient here, then assume that this side also transmission line is there. The length of that is tends to 0, very small length. That similar transmission line characteristic impedance Z0. Then here gamma is equal to the load impedance to this transmission line, very small length transmission line, is input impedance of this one. So that is Zin minus of characteristic impedance of this one Z0 divided by same thing you write and put the plus symbol here. So ultimately that is 300 minus 50 divided by 300 plus 50. So here this is 250 divided by 350, that is 5 times, it is 7 times. So the option is D, students. Right? That is the procedure. Now question number 4. If the reflection coefficient at the load is 0.6 at an angle of 60 degrees, that means gamma L is given, student. The reflection coefficient at the distance of lambda by 8 from load is, actually it is given like this. So what is the question? This is ZL. Here gamma L is given, that is 0.6 at an angle of 60. That means this is mod gamma L at an angle of e power theta gamma L is given. Now let us say this is the D is equal to 0 and D is equal to lambda by 8 length he has gone, and you have to find what is the reflection coefficient here. He is not talking of whether it is a lossy line or lossless line. If nothing is given, means you have to take it is a lossless line. Okay? Right. So gamma D is equal to mod gamma L e power minus 2 alpha D. e power j theta gamma L minus 2 beta d. Alpha value not given, so that is why you have to take it as a lossless line. So alpha value not given, so alpha value is not given, so consider the transmission line as lossless line. Okay, now you substitute all the things. Here beta d is equal to 2 pi by lambda into at what distance you want lambda by 8 distance. So lambda gone, you get pi by 4, and then 2 beta d is nothing but pi by 2, that is 90 degrees. That is 90 degrees in the degrees. So gamma d is equal to mod gamma L, that is 0.6, then e power 0, then e power j theta gamma L is 60 degrees minus 2 beta d is 90 degrees. So answer is 0.6 into e power minus j 30. Okay, e power minus j 30 degrees. So that is it is given like this, 0.6 at an angle of minus 30 degrees it is given. So option is B. Okay. Next question. Question number 15. Actually, it is a uniform plane wave question. But question number 15, 16, there is a similarity. You have to decide the direction of reflection coefficient. So that's why they are given here, no issue. I am reading the question, I am making the diagram, students. A plane wave, that means uniform plane wave. A plane electromagnetic wave propagating in free space. So first medium is actually free space, it is propagating, is incident normally on a large slab. So that means that medium 2 is incident normally on a lossless medium it is. So lossless medium means sigma to 0, and also it is non-magnetic medium. Non-magnetic medium, that means mu r2 is equal to 1. Dielectric material it is. So it is lossless, non-magnetic, dielectric material. That means definitely epsilon r2 is greater than 1. So for dielectric epsilon r2 is greater than 1. That means epsilon 2 is bigger than the epsilon naught. So because epsilon 2 is equal to epsilon naught, epsilon r2, epsilon r2 is greater than 1 means this is greater than epsilon naught. That's what he has given in the question. Maxima and minima are observed when the electric field is measured in front of the slab. So actually this is dielectric slab. स्लैब मतलब ऐसा पीस है, ये थोड़ा सा पीस है. It is some thickness is there for this. The maximum electric field is found to be 5 times the minimum electric field. So here V maximum is given as 5 times of V minimum is given. The intrinsic impedance of the medium should be, that means this dielectric medium, you have to find eta 2, you have to find, student. This you have to find. Anyway, this is a free space, then eta 1 is equal to 120 pi. Okay, right. Now, you know, eta 2 is equal to, this is the question I am solving here. Eta 2 is equal to eta naught divided by, anyway, student, once again I will write for your convenience, that is mu 2 divided by epsilon 2, that is root of mu naught mu r2 divided by epsilon naught epsilon r2, that mu naught by epsilon naught is eta naught. So eta naught is 120 pi, root of mu r2 is 1 epsilon r2. So that means eta 2 is equal to 120 pi divided by root epsilon r2. Eta 1 is 120 pi. This is 120 pi by root epsilon r2. Root epsilon r2, that means epsilon r2 is greater than 1. So this value is less than 1. So what is the conclusion, student? Eta 2 is smaller than eta 1. Eta 1 is bigger because this is 120 pi by root epsilon r2. This is 120 pi. Eta 1 is bigger. Now in this case, mm, gamma value should be negative. Why you know? Gamma is nothing but eta 2 minus eta 1 divided by eta 2 plus eta 1. This is the key point in this question. So eta 1 is bigger, that means negative, because eta 1 is greater than eta 2. So eta 1 is bigger, so negative value, that is. Let it be like that. Now he has given SWR is equal to, definition is voltage maximum divided by voltage minimum. He has given V maximum is equal to 5 times V minimum in the question it is given. So ultimately SWR 5 you get. Then mod gamma is equal to SWR minus 1 divided by SWR plus 1, dear students. So 5 minus 1 by 5 plus 1, that is 4 by 6 is equal to 2 by 3. Now gamma is equal to, magnitude is 2 by 3, but the sign is coming negative here. So minus 2 by 3, not 2 by 3. This is mod gamma it is. Gamma has magnitude and angle. So here minus 1 means angle is 180. That means 2 by 3 at an angle of 180. So 2 by 3 at an angle of 180 is nothing but 2 by 3 multiplied with e power j pi. E power j pi is minus 1. So minus 2 by 3. Now gamma is equal to eta 2 minus eta 1, eta 2 plus eta 1. Gamma is minus 2 by 3. That is equal to eta 2 minus eta 1 is 120 pi and eta 2 plus 120 pi. From this eta 2 value you get. So eta 2 value is 24 pi ohms you get. So this is the answer. So what is the issue in this question? The question issue is SWR is given, from that mod gamma you get. You will not get gamma value because gamma value has magnitude and sign also is there. Here you found that gamma is negative, so minus 2 by 3 is taken. Then you found eta 1 is given 120 pi, you found eta 2. So this is the one. And from this, if you want, you can find epsilon r also, you can find epsilon r 2 also, you can find. Next question number 16. Here the voltage standing wave pattern is given. Okay. Here it is given. This is a total voltage magnitude. This is actually total voltage magnitude at load is given. And you go away from the load, then he is saying this maximum value is 4 and this is the minimum value. So he has given this is the voltage maximum, total voltage maximum, and this is total voltage minimum, students. Anyway, this fellow is saying this is lambda by 2 and this is lambda. This already you know information. So minimum to minimum it is lambda by 2, and again next minimum to next minimum lambda by 2, so that it is lambda. That already you know. He need not to tell. वो बोलने का जरूरत नहीं, हमको मालूम है वो चीज. Now voltage standing, I am reading the question. The voltage standing wave pattern in a lossless transmission line with characteristic impedance voltage standing wave pattern means shape, pattern in a lossless transmission line having Z0 is equal to 50 ohm, having Z0 is equal to 50 ohm and a resistive load and a resistive load, that means RL, student, is shown. So the diagram is this one. This is the diagram. Find shown. Find RL value. That is the question. You have to find RL value. Students, given voltage maximum and voltage minimum, you can find SWR, dear students. Here at load something is happening. Can you tell me what is that? Voltage minimum came at the load. You see here, voltage minimum came at the load. At the load, impedance is RL. That is nothing but minimum impedance. Can you tell me why? Already we wrote that story, and you should not forget that statement. Wherever voltage is minimum, their impedance is also minimum impedance, because at the location of voltage minimum, impedance is minimum. So at the location of load, impedance is RL. That RL impedance itself becomes minimum impedance. So you students know that at the load, V minimum is present, and normalized minimum impedance, Z minimum, and normalized minimum impedance Z minimum is present. And already we have studied that normalized minimum impedance is equal to 1 by SWR. What is the definition of this one? Z minimum divided by Z naught, 1 by SWR. Now what is that Z minimum? RL, 1 by SWR. And you have to find RL. What is Z naught given in the question? 50. What is SWR? You calculate here. SWR is equal to voltage maximum divided by voltage minimum. That voltage maximum in the question is given as 4 volts at this location. Then this is 1 volt. That is 4 actually. So this is 4. That implies RL is equal to 50 by 4. That is 12.5 ohm. That is the answer. Option is C. Option C. Next question. A 75 ohm transmission line is first short terminated. Short terminated. Matlab load is that means short terminated means load is 0. So at the short circuit, student, already I told you, explained you, wherever short circuit is there, their voltage drop is 0. That is called minimum voltage. That means minimum impedance is there, current is maximum. So and the minima locations are noted. That you know. So terminated and minima locations are noted. When the short is replaced by a resistive load, that means when the short circuit, when the short circuit is replaced, short means short circuit, is replaced by a resistive load RL, the minima locations are not altered. That means once again minimum occurs at load only. So load RL, the minima locations are not altered or not altered. That means at the beginning the voltage minimum was at load when it is short circuited. Now that short circuit replaced with RL impedance. Now also minimum exists at load only. That means it is like previous question only. At the load voltage minimum is there. He has given story for that. Okay. The minimum locations are not altered. And VSWR is measured. And VSWR or otherwise SWR, ISWR all are same. 3. Find RL. After telling so much story, this is like previous question only. He is telling that at load V minimum is there. So at load V minimum is present, and at V minimum location Z minimum is present. So RL is equal to Z minimum. Once again I am telling, at load V minimum is present. Wherever V minimum is there, their impedance is minimum. That means that RL is equal to impedance minimum. Now already you know that normalized minimum impedance is equal to 1 by SWR, you know. And what do you say? The definition of this normalized minimum impedance is minimum impedance by Z naught. So that is equal to 1 by SWR. Now this Z minimum is nothing but RL. RL by Z naught is equal to 1 by SWR. So RL divided by Z naught characteristic impedance is given 75 ohm. That is 1 by SWR. SWR is given as 3. So RL is equal to 75 by 3. So RL is equal to 25 ohm. So that is the answer. Same as previous question, students. Previous question is given in diagram form. This question is given in theory form. So both are same. So students, next question. It is given in this question, two successive minimas were formed found also okay, at 17 centimeter and 27 centimeter along the length of the line, where VSWR is equal to 5. Calculate the reflection coefficient at the load. Calculate the reflection coefficient at load. You have to find gamma L. So that is the question. First of all, what is required? Gamma L, that is equal to mod gamma L e power j theta gamma L. Mod gamma L is equal to SWR minus 1, SWR plus 1. 5 minus 1 divided by 5 plus 1, that is 4 by 6, that is equal to 2 by 3. This calculation is over. Now we have to find theta gamma L. For that, some distance are given here. So if you take transmission line like this, here, let us say this is the load ZL. From the load at 17 centimeter, so 17 centimeter, he is saying V minimum is there, and again at 27 centimeter, V minimum is there. That means distance between minimum and minimum is lambda by 2. So lambda by 2 is equal to 27 centimeter minus 27 centimeter, 17 centimeter, that is equal to 10 centimeter. So this is 10 centimeter given. You know students, again you come here lambda by 2, that means here 10 centimeter. So you come here, that is 7 centimeter. One more V minimum comes. But here one more lambda by 2 you come, but not their transmission line, only 7 centimeter. That means this is the first voltage minimum. First voltage minimum. So first V minimum from load occurs at D minimum is equal to 7 centimeter. That means that is the D minimum. Okay. So this is D0, and so this gives D minimum. First voltage minimum is there. Now you students know that D minimum is equal to lambda by 4 pi and pi plus theta gamma L. So D minimum is 7 centimeter. Lambda by 2 is 10. From this lambda is 20 centimeter. So 20 into 10 to the power minus 2 divided by 4 pi plus theta gamma L. From this you calculate theta gamma L value, you get 72 degrees. So gamma L is equal to mod gamma L e power j theta gamma L, that is mod gamma L is 2 by 3 e power j 72 degrees. This is the answer, right? This information, using this information you can find mod gamma L. Using distances d minima, d maxima, using those d minima, d maxima distances, you can find theta gamma L. So reflection coefficient angle, then you can write the gamma. That is the concept of that question. Next, the reflection coefficient on a on a 500 meter long transmission line has a phase angle of minus 150 degrees. That is nothing but actually theta gamma L only. He is saying the reflection coefficient on a 5 meter long transmission line has a phase angle. That means theta gamma L is given. If the operating wavelength is 150 meter is given, that means lambda, what will be the number of voltage maxima on the line? So what will be the number of voltage maxima on the line? So this is the question. Now if you see here, there is one line, total length is 500 meter, it is given. Total length of this line is 500 meter. Okay. This is ZL anyway. Now what information is given, you can see theta gamma L is equal to minus 150, that is pi by 6, this is 30, so 150, right? Now operating wavelength lambda is given 150 meter. So if these two are given, you can find D minimum. So D minimum is equal to lambda divided by 4 pi plus theta gamma L, that is 150 divided by 4 pi, and pi minus of this is 5 pi by 6, theta gamma L is this much. Then from this D minimum value you get 6.25 meter. So make sure that student, always this angle should be in radian, student. Make sure, don't substitute the this angle in the degrees. Actually degrees given, I have converted to radian because this is in radian, denominator also radian. Radian gone, then you get the distance in meters. But don't substitute this in degrees, be careful. So radian, convert that to radian. Okay, this is 5 into 30 degrees. 30 degrees is pi by 6 radian. Okay, otherwise you will get wrong answer. By chance pi 150 degrees you put, you will get wrong answer. You keep observing the calculations also. Now first voltage maximum comes at D minimum plus or minus lambda by 4. Okay, some students might have got doubt. Now earlier I explained. Now once again I am explaining how to select D maximum. So D minimum is 6.25 plus minus lambda by 4. Lambda is 150 divided by 4. So if you take minus now, overall you get negative distance. So you should not take that. Then you have to take positive distance. So the positive value comes here 43.75 meter comes. Then here you can see D is equal to 0 here. Then when you go to D maximum distance, that is 43.75 meter. Then first time voltage maximum comes. First voltage maximum comes here from the load. Here when you get first voltage maximum, then 43.75 meter length is utilized. Then here after lambda by 2, after lambda by 2, you get V maximum. Now the question is, how many V maximums come in this length? Now it is very simple. Here number of V maximums is equal to number of V maximas on transmission line is equal to total length is how much? 500 meter. Then 43.75 meter na, 43.75 meter na, already one V maximum came. So you are subtracting 43.75 means in that length already one V maximum came. Then in remaining length, how many V maximas are there? So 500 minus 43.75. Distance between V maximum and V maximum is so here second V maximum distance will be lambda by 2, student, lambda by 2. So second V maximum lambda by 2. That is why you take here lambda by 2. So that is 500 minus 43.75 divided by lambda by 2, that is 150 by 2, that is 75. Plus 1 came already in 43.75 meters, 1 came. So ultimately this value becomes 6.08 plus 1, that is nothing but 7.08. The meaning is 7 times lambda by 2 plus 0.08 lambda by 2. So 7 V maximas are there, and in the remaining length there is no V maxima. So I am explaining whenever you get some fraction, you need not to take this one. So total number of V maxima is equal to number of V maximas on transmission line is equal to 7, you get. Okay, the option is D. Right? Next, question number 20. A lossless transmission line is connected to two identical voltage sources as shown in figure. a lossless transmission line is connected to two identical voltage sources as shown in figure. Okay, like this transmission line is there, and one side it is connected, it is like network theory concept, student, electrical circuits and networks. Both sides same voltage and same impedance is present for the source. Source voltage is same, source internal impedance is also, source voltage 100 at angle of theta, 100 at an angle of theta, internal impedance of source is 50-50, so 50 ohm, so same source is there. That is why both of them deliver same current. Now this is half length lambda L by 2, this is total length is L, so this is half of the length and this is half of the length, total length is L. Now he is calling this as A dash locations. The impedance measured at the midpoint A dash of the line. So then find impedance at A dash locations. He has called this A location. A dash you call A at A dash location. Then answer is what? Infinity. Why? Because let us say current here, because of this source is I, then because of this also you get same current. Why? You know, this source voltage, this voltage same, internal impedance same, and the length same. If I current comes like this, here also I current comes. So overall current is 0 here. So impedance is equal to total voltage divided by current. So here V divided by voltage here divided by total current. So I total at that location is I minus of I. So that is equal to V by 0. You get infinity. So at this location voltage is V, and at this location current is 0, total current. So you get infinity. So option is A. It is like network theory. Okay. Next, we will start the theory, and after that we will solve these questions. Now let us see water wave transformer matching. We will discuss that one, impedance matching. If you recall the lambda by 4 transmission line, so this is lambda by 4 length, then Z0 is the characteristic impedance ZL. Now the input impedance of lambda by 4 is Z0 square by ZL. If ZL 0, then Zin of lambda by 4 is equal to Z0 square by ZL is 0, you get infinity. That means here ZL 0, for example, here it is infinity input side. That means it converts low impedance to high impedance. For example, if we put infinity here, then here we get 0 here, 0. That means it converts lambda by 4, converts low impedance to high impedance to low impedance. That means it behaves like impedance converter. For example, here this is 50 is there and this is 100 is there. Now answer is 50 into 50 divided by 100, that means it is 25. So here it is 100 is there here. After lambda by 4 distance, impedance become 25. So this is impedance transformer. Transformer means changing. Impedance is changing. It is able to change one impedance value to other impedance value. So that is why this property of the lambda by 4 transmission line is used in impedance matching technique. So that is called quarter wave transformer impedance matching. Okay. So QWT, that means quarter wave transformer, QWT, impedance matching. Okay. First you see the situation. Already I wrote this. This is lambda by 4 transmission line. Already I wrote this previously. Once again I am writing. Let us say characteristic impedance is ZQ for this. Now here the load impedance is Z2. Now the input impedance is Z1, let us say. This is lambda by 4. For this transmission line, Z1 multiplied with Z2 is equal to ZQ square. Already you know this. Okay. Here Z1 is input impedance of lambda by 4 transmission line. Similarly, Z2 is load impedance of lambda by 4 transmission line. ZQ is characteristic impedance of lambda by 4 transmission line. Okay, this is regarding the lambda by 4 transmission line. So I will draw the diagram here and I will be writing anyway. Let us see the diagram now. Here there is one transmission line that is called main transmission line. Like this one transmission line is there. Okay, so that is called main transmission line. Here for this transmission line, this is called main transmission line. The characteristic impedance is Z0. Of course, this Z0 can be written anywhere. So for this transmission line, characteristic impedance is Z0. Then load impedance is ZL. I am writing this Z0 here, students. I wrote that there. No? Okay. This is the main transmission line. Characteristic impedance is Z0. Now, what is the reflection coefficient at load? Gamma L is nothing but ZL minus Z0 divided by ZL plus Z0. Now, ZL and Z0 are not same. That is why there exists a gamma L, and gamma L is not 0. Reflection is present here. If reflection is present, then standing wave ratio is also present here. 1 plus mod gamma L divided by 1 minus mod gamma L. So this is 1 plus mod gamma L divided by 1 minus mod gamma L. So one objective question is, on the main transmission line, before matching the impedance, what is the reflection coefficient? Answer ZL minus Z0, ZL plus Z0. What is SWR? 1 plus mod gamma L, 1 minus mod gamma L. This is like a usual formula, right? This is modulus. Now the discussion is, what is the problem if there is a reflected wave? The problem is here you will have a microwave generator, and that microwave generator is like tunnel diode, etc. These tunnel diodes are very sensitive. If any signal coming here transmission line enters the tunnel diode, then frequency of the tunnel diode changes. Sometimes it is heated up and it is burns off. That becomes unstable microwave generator. So that is why there should not be any reflected wave here. So there should not be any reflected wave. That means somewhere you should stop the reflected wave. For that we use lambda by 4 transmission line. Okay. Now let us say from the load at some distance we have connected the lambda by 4 transmission line. Okay, so let us say here, and this main transmission line is removed, and after removing this main transmission line, and we are connecting the lambda by 4 line here like this, and here this lambda by 4 transmission line is connected here. Why we are connecting here? So that here matching is done and here there is no reflected wave. That is the purpose. So the length of this is lambda by 4 here to here. Okay. Now characteristic impedance of this is ZQ. Now this is also main transmission line. Characteristic impedance is Z0. This one and of course this one, both are main transmission lines. Okay, this one is also main transmission line. Main transmission line. Main transmission line means it is used to transfer energy from signal source to the load. Here antenna is there. So that is this is also main transmission line. After completing this, I will write here also main transmission line. Now, what is the meaning of QWT impedance matching? I will tell you the statement. I told the question. Now I will answer that question. What is the meaning of QWT impedance matching? That is the question. And after some time I will tell you the answer. Now before analyzing that, you have to answer the questions now. This is some length is there for this transmission line. If this transmission line has some length, definitely it has some input impedance here. So this transmission line has input impedance. Let us say how much input impedance, Z2 impedance is there. The input impedance of this transmission line behaves like a load impedance to this lambda by 4. So Z2 is load impedance to this lambda by 4 transmission line. Once again, here if you see, the input impedance is present for this one and for this one. We are calling that input impedance as Z1. So here Z1 is input impedance at lambda by 4 line. So Z1 is input impedance of lambda by 4 transmission line. So at this location, whatever impedance is there, that is the input impedance for this total section. That means at the location of lambda by 4, the input impedance is Z1. You are saying Z1. We are saying. Now, what is Z1 multiplied with Z2? So this is the formula. So Z1 multiplied with Z2 is equal to ZQ square. So this is equation number 1. This is 1 point over. Can you tell me what is the reflection coefficient at this location, student? Reflection coefficient at this location. I will write here. Reflection coefficient at this location. Just exactly here. Reflection coefficient gamma. I will write gamma, or otherwise gamma dash I will put. So this is gamma L. I will write this as a gamma dash at this location. थोड़ा सा ये ऐसा हो गया क्या? ठीक है, कोई बात नहीं. This is up to here. This is up to here. So this impedance is Z1. Okay, exactly these two have same length. That's what I want to say. Okay. Now gamma dash at this location is equal to the input impedance. Otherwise gamma at this location is equal to the load impedance to this section, that is input impedance of this section, that is Z1, minus of characteristic impedance of this section, that is Z0, divided by Z1 plus Z0. Okay. Dear students, here on this transmission line, we don't want reflected wave, because if reflected wave enters into the signal generator, then that becomes unstable. That is why we want to stop the reflected wave here. So then how to stop the reflected wave? If you do some design here in such a way Z1 becomes Z0, then gamma dash is 0, then there is no reflected wave here. Okay. So students, gamma dash is equal to Z1 minus Z0 divided by Z1 plus Z0. If we design lambda by 4 transmission line, that means designing means you adjust this ZQ value, keep changing ZQ value. I will tell you that, keep changing ZQ value. So if we design lambda by 4 transmission line in such a way, Z1 becomes Z0, Z1 becomes Z0, then gamma dash becomes Z0 minus Z0, Z0 plus Z0, 0, so that there is no reflected wave on main transmission line from source to lambda by 4 transmission line. That means from source to lambda by 4 transmission line means on the main transmission line reflection is not there from source to lambda by 4 line. So that means here gamma dash is equal to 0. So here SWR is 1 plus 0 by 1 minus 0. So 1 plus mod gamma, 1 minus mod gamma, you get 1. So there is no reflection coefficient. Matching is done. Matching is done there. Now start the design. That is the requirement actually. अभी तक हमने रिक्वायरमेंट के बारे में बात किया. Z1 हमको Z0 चाहिए. अभी शुरू होता है डिजाइन. So put Z1 is equal to Z0 in equation 1. Then if you put Z1 is equal to Z0, then only matching is done. So Z0 into Z2 is equal to ZQ square. So this is equation number, you say 2. I am giving a hint here. Z2 is equal to ZQ square by Z0. In general, this is real value. This is also real value for lossless transmission lines. Root L by C, they are real value. So this is real value. That means where to position this lambda by 4 line from load. So here wherever Z2 is there, their impedance should be real. So now this is D is equal to 0. At which location this lambda by 4 line is located from the load? Let us call that distance as a DQ. D means distance, Q means quarter wave transformer. So at which distance it should be placed from load, that is also to be calculated. So where to put that? At a DQ distance. Then what should happen at a DQ distance? At a DQ distance, the length of the transmission line should be, Z2. That Z2 should be real. Now the answer, on this transmission line, wherever voltage is minimum or otherwise wherever voltage is maximum, at that location impedance of the transmission line is real impedance. On the main transmission line from the load, wherever first voltage minimum comes, wherever first voltage maximum comes, then at that location impedance is real. So whenever impedance is real, at that location we put this lambda by 4 transmission line. Now what is the meaning of design? Design means you calculate a dq distance. That means at which distance you have to put this transmission line lambda by 4 line from the load, and then what is the value of dq? It should be not dq, zq. So find the equations of dq and equation of zq, then that is called the design of qwt impedance matching. So if zq can be changed, because if you keep changing the medium between these two conductors, then zq value keep changing. Okay, medium parameters change, then zq also changes. So already written here, zq means characteristic impedance of the lambda by 4 transmission line. Here it is written. Now at dq distance, impedance of at dq distance, impedance of input impedance, na? At dq distance, input impedance of transmission line is Z2, which is real. At the locations of V maximum, V minimum, at the locations of V maximum, V minimum on transmission line, the impedance is real. So lambda by 4 transmission line is lambda by 4 transmission line can be located at first V minimum or first V maximum from load. Which one is preferred? Voltage maximum or voltage minimum? Whichever is near value, that is preferred. For example, one transmission line is given. For that we calculate V minimum, we got 4 meter, V maximum we got 10 meter, then 4 meter is nearest, then we try to reduce the reflections nearest to the load. Then for example, in one question V minimum is 10 meter, V maximum is 4 meter, then where to put that? At the location of V maximum we put, because nearest to the load is V maximum. Now what is the meaning of design of this? Find dq equation, then you can find at which distance to put the lambda by 4 transformer, and then find zq value, or otherwise find zq equation also. That is called the design of the lambda by 4 matching. Now case 1, if we put lambda by 4 transmission line at the location of first V minimum from load, then dq is equal to d minimum, then dq is equal to d minimum is lambda by 4 pi, lambda by 4 pi plus theta gamma L. This is the equation of this dq, that is equal to d minimum. This is the equation. Now at the V minimum location, the normalized minimum impedance is present, and which is equal to 1 by SWR. So that means Z minimum is equal to, what do you say, 1 by SWR. That means this is minimum impedance by Z0 is equal to 1 by SWR. Now at the location of DQ, the DQ is D minimum, the impedance present here is Z2. So Z2 by Z0 is equal to 1 by SWR. So dear students, this design is like this. Here, if you want, I will draw the diagram here. Now that this is ZL, this is D0, and now at a D minimum location, we kept this lambda by 4 line. So this lambda by 4 line is kept at D minimum distance. So here, now at the location of D minimum, we are calling the impedance as Z2 because here V minimum is there now. At the location of voltage minimum, that impedance is minimum. So that is why this Z minimum is nothing but Z2 only now. Okay. So from this Z2 is equal to Z0 divided by SWR. Let us say this is equation number 2 is there. So this is 3, this is 4. Now put equation 4 in equation 2, here Z2 is there. So Z0 into Z0 divided by SWR is equal to ZQ square. Now we got the equation of ZQ, that is Z0 by root of SWR. So this is the answer to the ZQ. Now I am telling you what is the meaning of design. Calculate DQ, at which distance you have to put that lambda by 4 transmission line. If you want to calculate this, you need one formula. The formula is lambda divided by 4 pi plus theta gamma L. So how you get theta gamma L here? Gamma L is equal to ZL minus Z0 by ZL plus Z0. You take the angle of that, put that angle here in radians. And similarly, you take gamma L, then where SWR is equal to, where SWR is equal to 1 plus mod gamma L divided by 1 minus mod gamma L, dear students. So gamma L is ZL minus Z0 by ZL plus Z0. Already I have calculated there. Then what is second option? Case 2. So case 2 is if we put lambda by 4 transmission line, that is a quarter wave transmission line, at the location of first voltage maximum from load, then dq is equal to d maximum. Yes or no? Then what is the d maximum formula? That is equal to d minimum plus or minus lambda by 4. Already you know that. So that is the formula, right? Now this is the equation number 6. At the V maximum location, that means wherever you put the lambda by 4 line, now V maximum is present. So at the V maximum location, the normalized maximum impedance, the normalized maximum impedance is present, which is equal to SWR. Okay. Now normalized maximum impedance is equal to SWR, that is nothing but capital Z maximum divided by Z0 is equal to SWR. And this Z maximum, if you want a diagram, I will draw here. So this is ZL, here D0. Now at D maximum, we are putting that lambda by 4 transmission line like this. So lambda by 4 transmission line like this. Okay. Now here voltage maximum is there. Now we are calling this impedance as Z2. Now that Z2 should be equal to Z maximum, because at the location of Z2 here voltage is maximum. So Z maximum is nothing but now Z2, that is SWR. Then Z2 is equal to Z0 into SWR. Let us say this is equation number 7, and put equation 7 in equation number 2. Now Z0 into Z2 is Z0 SWR is equal to ZQ square, and ultimately that implies ZQ is equal to Z0 root SWR. So this is equation number 8. So if you put lambda by 4 transmission line at a D maximum location, then that dq is equal to D maximum. That is the formula. And then what characteristic impedance lambda by 4 line you have to select. The characteristic impedance of that lambda by 4 line should be equal to Z0 characteristic impedance of main transmission line multiplied with root of SWR, where SWR is 1 plus mod gamma L by 1 minus mod gamma L. This is the design. Now, what is the advantage of this? You can send the frequencies at the input which are integer multiple, which are odd multiples of lambda by 4, because for example lambda by 4, 1 into lambda by 4 you have designed. Now for example you send the frequency in such a way that is 3 times lambda by 4, that is no problem. 2 times lambda by 4 plus 1 into lambda by 4. Now this is lambda by 2. That lambda by 2 behaves like again repeated. So once again it is lambda by 4 only. For example 5 times lambda by 4, that is actually 4 times lambda by 4 plus 1 time lambda by 4. So this is integer multiples of, this is lambda, integer multiples of lambda by 2, that is so that is why once again it is lambda by 4. So that is the advantage. Once if you design this quarter wave matching for lambda by 4 length, then it works for odd multiples of lambda by 4. Then what is the disadvantage? If you design this for particular frequency, f is equal to 100 megahertz frequency, then according to this lambda by 4 value you can calculate c divided by, for example if this is air medium is there, then c divided by f into 4, then you will be calculating this lambda by 4 value. For example this is 3 into 10 to the power 8 divided by 10 to the power 8 into 4. So ultimately 3 by 4 meter should be their length of this. For this if you put 3 by 4 meter length, then this matching is done at 100 megahertz frequency. Now I am not changing the length of this. If I change the frequency to 100.1 megahertz, then a slight change in lambda, so it works for that. Then 99.99 megahertz, then also frequency is little bit changed, so lambda is little bit changed, but same length works for that also. But so this is C, dear students. So actually light velocity. So if you change, first we have calculated this lambda by 4 for 100 megahertz. But if I change so much frequency, 50 megahertz I will send, then there is so much change in lambda by 4. If I put 3 by 4 only, it won't work. That means this lambda by 4 matching works for narrow band frequencies only. Narrow band means a bandwidth can be very small. Narrow band frequencies only. That too, it works if load is real. So for real loads only it will work. So that is why if you want to do matching for broadband frequencies and load is complex, then we go for stub matching, single stub matching, like that. So I will write these points there. Okay. So here lambda by 4 matching lambda by 4 impedance matching works for odd multiples of lambda by 4, works for odd multiples of lambda by 4. So that is lambda by 4. That means if frequency matches with lambda by 4, otherwise 3 lambda by 4, or otherwise what do you say, 5 lambda by 4 dash dash dash, like that it works. Okay. What is the meaning of this? If you want, if I take lambda is equal to V by F, V by F, then it is V by F into 4, this one. Now this is lambda is V by F. So now this can be written as V by F, okay, V by 4F. Of course, here 3 is there. That 3 can be written as F by 3 here. So that means for that frequency also it works. That is the meaning of that. That means you can change the frequencies in such a way for those frequencies the length can be lambda by 4, otherwise 3 lambda by 4, otherwise 5 lambda by 4, like that. So one gate question is there, student, based on this in previous papers. You can solve that one. You have to select the common lambda by 4 for two frequencies. So to solve that question, this is the point. Okay. So if you want here checking 3 lambda by 4 is nothing but 2 times lambda by 4 plus lambda by 4. That is equal to, this is lambda by 2 plus lambda by 4. Once again after lambda by 2 repetition is there. So this is lambda by 4, like this example here. This is again equal to lambda by 4. You put this in the box. Lambda by 4 impedance matching works for odd multiples of lambda by 4. That is this one. Odd multiples means this one. Now here one more 2 more points I will write here. Lambda by 4 matching, lambda by 4 matching, impedance matching, that is lambda by 4 matching works for narrow band frequencies, works for narrow band frequencies. Okay, next one. QWT impedance matching is suitable for real loads. That is why if you want to match complex loads, then you have to use stub matching. So what is the meaning of stub? Small length of the transmission line. So stub means now we will talk of stub actually. Stub means here small section of transmission line. Small length is called stub actually. So there are two types of stubs, open stub and short stub. Short, SHORT, short stub means the load is short circuited, that is the meaning. So here stubs are two types, short stub and open stub. Case 1, short stub, that means actually the meaning is that is that is load is short circuit. That is the meaning, student. Short stub means. Now we will take lossless transmission line. For lossless transmission line, you take LT, that means length of stub here. Of course, L means length, T means transmission line. So this stub is nothing but small length of transmission line. So LT here is length of the stub. So this one is short circuit now. ZL is equal to 0. Short circuit is there. Characteristic impedance of this is Z0. Then D is equal to 0 here. Now for the input, D is equal to LT you have to put. Now what is the input impedance of short circuit ZNSC? So simply I will call this as a ZSC, student. Input impedance when load is short circuit. Okay. Already you know the formula. The formula is this one. Z at a D distance is equal to Z0 ZL plus JZ0 tan beta D divided by ZL plus Z0, no? Z0 plus JZL tan beta D, and if you substitute D is equal to length of the transmission line and substitute ZL is equal to 0, so that becomes Z0 0 plus JZ0 tan beta LT divided by Z0 plus 0, Z0 Z0 cancel. So this we call it as a ZSC. Now Z in, or otherwise this we will call it as a Z in only. Okay, Z in of this I want to, okay, I will call it as ZSC only, student. ZSC for what is this? J Z0 tan beta LT length. So can you tell me this is for how much length actually? For LT length actually. For LT. Okay, let it be like this. So this is ZSC. Here equation number 1. Now if you want YSC, this is impedance, this is admittance, that is 1 by ZSC. That implies YSC is nothing but 1 by JZ0 tan beta LT. So that is minus J cot beta LT divided by Z0. Let it be like this. So this is equation number 2. If you remember this, no need to remember this. If you want admittance, then 1 by impedance. So this is short circuit stub. Stub means some length of transmission line. So case 2, open stub. Actually open stub means that is load is open circuit. That is the meaning of that. So if you take length of the transmission line is LT here and characteristic impedance is Z0, then load is open circuit, ZL infinity open circuit. D0 means at load. D is equal to LT. Then once again this is ZOC, that is nothing but input impedance only, ZOC. So I am using symbol ZSC, ZOC, no problem, ZOC. Here ZOC, if you want you can write ZOC is the input impedance of open circuit stub. That is the meaning of this. So here what is impedance at D distance? I will write like this, Z0, this is the formula, Z0, and 1 plus J Z0 divided by ZL. I am pulling out ZL in numerator and denominator. So ZL cancel. Then here ZL by Z0 plus J tan beta D. So in numerator and denominator we are pulling ZL. ZL cancel. Here ZL comes, here ZL comes, like this. Okay. This is original formula. In that formula, let us substitute D is equal to LT and ZL is equal to infinity. Then this becomes 0, this becomes 0. So you get Z0 1 plus 0. Why to write unnecessary all the terms here? ZL infinity means this is 0. This is also 0. So divide by 0 J tan. You have to substitute D is equal to LT. So beta LT. We are calling this as a ZOC, and this is here minus J. 1 by J is minus J. Then Z0 1 by tan is actually cot beta LT. So let us put this in the box and let us call this as equation number 3. And if you want admittance YOC, that is 1 by ZOC, that implies YOC is equal to 1 divided by minus JZ0 cot beta LT. This is equation number 4. So we are ready to go to stub matching. Before going to stub matching, we must know what is the input impedance or otherwise admittance of the open circuit stub and short circuit stub. We must know. And here one important point I am telling you. What discussion is going on here? क्या चल रहा है इधर? We can change LT here. Change LT value, increase this. Here actually one short circuit line is there that you can slide like this. उसको ऐसा slide कर सकता है. If you slide this, then for example this short circuit you slide here, then length becomes this much only. You slide here, length becomes this much only. You can change the length there. If you change the length, then this angle changes. Then if this impedance value changes, so this is the mechanism where you can change the impedance. In impedance matching, we have to change the impedance. Now, next point. This open circuit, at these terminals, radiation starts. Wherever open terminals are there, radiation starts. This also behaves like a small antenna, it radiates. Here we are going to use these stubs for matching purpose, but not for radiation purpose. We are going to use these stubs for matching impedance matching purpose, but not for radiation purpose. So this open stub unnecessarily radiates. It behaves like a small antenna. That is why in impedance matching, short stubs are preferred. That is also one of the objective question. The statement is like this. Short stubs are preferred to open stubs. That means short circuit stubs are preferred, given preference, because open stubs are liable to radiate. Liable to radiate means they start radiating. That is an important objective question. I will write here. Short stubs are preferred to open stubs. The meaning is short circuit stubs are used compared to open stubs. That means we don't use these open stubs. So short, what is written here? Short stubs are preferred to open stubs because open stubs are liable to radiate. Open stubs are liable to radiate. This is also important statement, students. Now once I told you, anyway this we are not going to use now, we will use this. What is the input impedance of this JZ0 and beta LT? Then can you change the impedance? Yes. How to change the impedance? Keep changing length of the transmission line, then impedance can be changed. So we are going to use this in impedance matching for complex loads. That is called single stub matching. If a single transmission line is used in the main transmission line, then that is called single stub matching. If two are used, double stub matching. So anyway, they never asked these stub matching questions, but कोई बात नहीं, हम डिस्कस करेंगे उसको. अभी तक कोई पूछा ही नहीं है क्वेश्चंस, बिकॉज ये completely practical oriented है ये. So we will discuss single stub matching. Students, you write this in the notes. Note more clearly. I told you lambda by 4 impedance matching works for multiple frequencies. I told you 2-3 frequencies you can send with a single length, then so that their quarter wave lengths are odd multiples of lambda by 4, such as lambda by 4 to lambda by 4, like that. So there can be multiple frequencies. I told you in GATE book, previous papers, one question is there. You solve that one, you can understand that one. Solution it will be given in the book. Now let us discuss what is a single stub matching. Single stub matching. I am going to draw the diagram here. You can see the diagram. Here one main transmission line is there, like this. One main transmission line is there. I will draw a little bottom because I need to write the stub here. So for that I need some place, student. ऊपर stub लिखेंगे. So this is the main transmission line. You have to do matching here. These are conductors of main transmission line, two conductors. Here the load impedance of that is ZL, because I want to write something here also, so that big letters, no, bada letters आपको दिखेगा अच्छे से. So this is ZL. The characteristic impedance of this is Z0. Now can you tell me what is the reflection coefficient here? Gamma L is equal to ZL minus Z0 divided by ZL plus Z0. That is also objective question, student. We are going to do stub matching here. Now before stub matching, between the stub and the load, what is the reflection coefficient? What is the SWR? That is also objective question. So now SWR is equal to 1 plus mod gamma L divided by 1 minus mod gamma L. So you have to calculate this. But anyway, if ZL and Z0 are real, then if ZL is greater than Z0, then directly SWR is equal to ZL by Z0. Bigger one by smaller one, if they are real. Now here there is a reflected wave because impedance is not matched here. In general, Z0 is characteristic impedance, ZL is input impedance of antenna. So the input impedance of antenna and this one not matched actually. That is why I told you there should not be a reflected wave here, because here source will be there. If reflected wave goes into the source, then that becomes unstable. We have to stop that reflected wave. Now here somewhere I will use this stub. I will connect that stub for matching purpose. So here at this location I am connecting one stub here like this. This one. Now that is actually short circuited. So ZL of this is 0, it is short circuited. the length of this is called LT. Already we know the input impedance of this LT. So the input impedance is called as Zin of LT. The admittance is called as Y in LT. So Y in, I will not write both of them. I will write only Y in LT. Okay. Because for parallel, these two, for parallel admittances are added. So this is Y in of LT. So input admittance for LT length. This is a short circuit stub. Now impedance matching is done here using this. That is why it is called short stub matching. This is D is equal to 0 means at load. Now from the load, we have placed this at LS distance. Actually the meaning of LS is L means location, S means stub, location of the stub, or otherwise length of the stub from the load where it is placed. That is the meaning. LS means, I will write that. Now here this what do you say, here actually it is here, but I am writing here, this is Y in of LS. That means input admittance for LS length of the main transmission line. This is called main transmission line. Now what is the Y in of both the transmission lines? So Y in is equal to, because they are parallel, here current goes, that is divided like this and divided like this. So Y in is equal to Y in of LT plus Y in of LS. Y in of LT means input admittance of LT length. Y in of LS means input admittance of this LS length transmission line. So that is Y in. Now the input impedance, if you want input impedance of these two, that is 1 by Y in. Okay. Now I will write here what is LS. LS means length of location, or otherwise I will do one thing, distance from load end at which stub is placed. That is the meaning. LT means length of short circuit stub. Now dear students, here one thing is there. The characteristic impedance of this is also Z0. The characteristic impedance of this also Z0. Both can have same characteristic impedance, because here matching is done by changing the lengths, not the characteristic impedance, student. So matching is done by changing the lengths. So anyway, can you tell me one more objective question? What is the standing wave ratio here? 1 plus mod gamma L divided by 1 minus mod gamma L. Can you tell me what is the standing wave ratio here? I will write the standing wave ratio of that standing wave ratio of this after discussion. If you want standing wave ratio of this one, this is short circuit, na? For short circuit, here gamma L is equal to ZL minus Z0, ZL plus Z0. So ZL is 0. So this ZL is 0. 0 minus Z0, you get minus 1. So mod gamma L of this is actually, no need to calculate, I know that, but for your convenience you have to observe, that is mod gamma L is 1. So SWR is infinity for this. We are not bothered what happens to standing wave ratio of this. We are not bothered. We are asking that to match the impedance. उसका वैल्यूज क्या है हम लोग ध्यान नहीं देता है, लेकिन उसका पर्पस है, उसको बोल रहे हैं हम, आप इधर रहो, हम इम्पीडेंस मैचिंग करना है करके बोल रहे हैं, उतना ही है बस. Okay, now let us give the statement. What is the meaning of stub matching? You calculate LT and you calculate LS, then stub matching is done. That is the meaning. You give the formula for LT and you give the formula for LS, then stub matching is done. Now, dear students, actually this is main transmission line, and some length of that is taken here. That is why this characteristic impedance same. Here also characteristic impedance of this line is also Z0 only. I will write here. So this is main transmission line. Okay. Now I will write the impedance of this. Impedance of transmission line at D distance from load is Z of D is equal to Z0 ZL plus JZ0 tan beta D divided by Z0 plus JZL tan beta D. So here students, if ZL is complex, then Z of D is also complex, having real and imaginary values. If D changes, then tan beta D value changes. So real and imaginary values change. That means this Z of D is having a real impedance plus or minus J, imaginary we don't know whether it is plus or minus J, whatever it might be. So it is okay, I will do like this. Change, then I will do one thing. Y of D, yeah, Y of D. Y of D is equal to 1 by Z of D. That means if this is complex, 1 by complex is complex, so this is also complex. Then this Y of D has real value plus minus J imaginary value. Okay. That means these values keep changing. Let at LS, that means this one, मान लीजिए at LS, let at LS distance from load Y of D, okay, this formula anyway, let at LS distance from load Y in of LS, that means this formula only, if you substitute D is equal to LS na, this distance is equal to LS na, then we get input impedance of this LS length actually. So let at LS distance from load Y in of LS, that means this one. Once again I am telling D is equal to 0 here. Now D is equal to LS you put, then in this formula D is equal to, actually in this D is equal to LS you put 1 by ZD LS gives Y for LS distance, that is called as Y in of LS length. So let at LS distance from load Y in of LS Y in of LS real part is Y naught, of course that is equal to 1 by Z naught, is Y naught. That means Y in of LS has real value y naught, actually you start here, keep going, जाते रहो ऐसा. Whenever y in of ls admittance value real part becomes y naught value, that y naught is 1 by characteristic impedance of this transmission line, then you stop there. After stopping at that location, there you have to put this short stub. So that means you have to get the equation for this ls, then you can find that distance. So y in of ls is equal to y naught. Now we are not bothered about this imaginary part. वो जितना भी रहने दो, कोई टेंशन नहीं है, उसको कैंसिल करवा देता है. So let us say that has a plus minus j b. So this is 1 by reactance, that is susceptance actually, plus or minus jb. So this is equation number, you say equation number 1. Till now what discussion is going on? You start at D, keep going on this transmission line, जाते रहो. Then impedance real part and imaginary part keep changing, and the admittance real part and imaginary part keep changing. Then at one location you got real part of the admittance value is equal to y naught, then you stop there. So let us assume that at ls distance you got a real part of the admittance is y naught, then you stop there. Then there we have to connect the short circuit stub. Now the question, what is the equation of ls? Then you substitute in this d is equal to ls, then you take reciprocal of that, then you separate the real part and imaginary part, equate that real part to this y naught, then you get the equation of ls. Okay, so I am writing that answer now. After solving we get ls is equal to lambda by 2 pi tan inverse of z naught divided by z naught of this transmission line and zl of this transmission line. Modulus is taken under root. So this is the formula of that one. No need to do the derivation. So after solving we get actually ls you substitute d is equal to ls. Then z in of ls you get. Then take reciprocal. Then after taking reciprocal, find the real part of that, equate that to 1 by z naught, then you get this ls. Okay, you got this one. Now you found ls. The input admittance of short stub is y in of LT for LT is equal to 1 by Z in of LT. Already I have written in a previous discussion that Z in of Y in of LT is equal to, what is Z in of LT for short circuit, that is J Z naught tan beta LT. This is JZ naught tan beta LT is actually input impedance of short circuit stub. So that we are calling it as a Z in of LT. Okay, students. So here now this is what do you say, equation number 2. If you want here I can write, because Z in of or otherwise ZSC short circuit stub input impedance is JZ naught tan beta LT. In previous topic we have written. So that Z in of SC we are calling it as a Z in input impedance for LT length. So 1 by Z in LT, that Z in LT is this one. 1 by Z in LT is nothing but Y in of LT. Okay. Now I told you what is the meaning of design of this single step matching. Design means find LS value. If you want to find LS value, then you need one equation. So this is the equation. They give frequency of operation. Then if air medium is filled, then lambda is equal to C by F. Then you can calculate lambda value. Then for this Z0 is given, ZL is given. You take this so that you get LS. Okay. You get LS. That means LS equation is known. Now you have to find LT equation. LT equation. So anyway, dear students, I am asking one question now. Can you tell me what is gamma here at this location? Or otherwise here also you can write, here also you can write, doesn't matter. Gamma of this line is equal to input impedance of this minus characteristic impedance of this divided by Zin plus Z0. You can write this here also, no problem. Gamma of this transmission line is equal to input impedance of this line, these two lines behaves like load impedance to this one. So Zin minus Z0, Zin plus Z0, where Zin is equal to 1 by Yin. Right. Now select LT length, or otherwise calculate LT length in such a way Y in LT, this value is equal to, here in this plus or minus j beta is there, opposite of that minus plus jb. That means for example, let us say here plus minus j10 came na, then you have to take minus plus j10, you have to take y in of LT is this one, that is what do you say, equation 3. Put equation 2 in 3. Actually I brought this, I got this from this equation, opposite of that I have taken. Then I have to write this equation, this one. So here 1 by jz0 tan. Do you know what is beta value? Beta is 2 pi by lambda, then LT. So this is equal to minus plus jb. So dear students, here for example plus minus j10 came, then minus plus j10 10 you have to take. Z0 will be given. Lambda is C by F if it is air filled. Then epsilon r mu r of the medium between the conductors is given. Then V by F, where V is C by root mu r epsilon r. Then from that lambda also known. Only unknown will be LT here. From this equation you will be finding LT. How can you find LT? Take the reciprocal, then tan comes to numerator, or otherwise cross multiply this. From that 2 pi by lambda LT is equal to some tan inverse you get, like that you will be doing. So after that you will find LT. So select LT length in such a way, this is equal to this one, and from this you will be selecting. So this one you have to remember, student. So this one you have to remember. This is the equation. Let us say I will write this as equation 4. So equation 4 gives LT. Okay, equation 4 gives LT. Okay, so I told you what is the meaning of design. Find LS value, that means from this equation you will find LS value. For example, let us say 10 meters you got, then from 10 meters you will not get, maybe you say let us say 0.5 meter you got, then from load 0.5 meter you connect this. Let us say LT value from this equation is 0.6 meter, then here 0.6 meter you have to take. And then now design is over, that much only. You know why? After this design, y in of y in is equal to, now y in is equal to already y in means the total input admittance of these two lines. So y in of LS plus y in of LT. So y in of LS plus y in of LT length. So that is y in of LS is from equation 1 let us say this equation 5. So put equation 1 and equation 3 in equation 5. So now yn is equal to, what is yn of Ls from this? Y naught plus minus j b, and from this one yn of Lt is equal to minus plus jb. So ultimately this cancel. That is the purpose of that short stub. वही है उसका पर्पस. वो शॉर्ट स्टब का पर्पस है स्टूडेंट्स, शॉर्ट स्टब का पर्पस है वाइन ऑफ एलएस में जितना भी रिएक्टिव पार्ट होगा, मतलब जितना भी ससेप्टेंस पार्ट होगा उसको कैंसिल करना है इधर. तो वही है उसका पर्पस, कैंसिल हो गया. सो नाउ yn is equal to y naught, that implies Zin is equal to 1 by Yin. So now Zin is equal to 1 by Yin is y naught. So that becomes Z naught. 1 by y naught is Z naught. So Zin is equal to Z naught. I will call this as a gamma dash here. So that because so many gammas are there, no, that is why gamma dash. Now that gamma dash is equal to Zin minus Z naught divided by Zin plus Z naught. So ultimately this gamma dash has become Z naught, Z naught, Z naught, Z naught, 0. So gamma dash 0, that means matching is done here this side. So here this side na gamma dash is 0. Now SWR is equal to 1 on this transmission line. Okay, matching is done. Now dear students, now objective questions, they don't ask all these equations till now. They did not ask student, but I have discussed. Anyway, I am asking one question, you answer. In the single step matching diagram, what is standing wave ratio here? Then answer 1 plus mod gamma L by 1 minus mod gamma L. They give the value of ZL and they give the value of Z0, and you can calculate that this gamma L, take the mod of that, you get this one. Next question, what is the, in single step matching, what is standing wave ratio of this short stub? Answer infinity, because short circuit or open circuit always SWR is infinity. Then what is the standing wave ratio on the main line before the stub iske pehle towards the source, then SWR is 1, matching is done there. So this is all about the single stub matching, dear students.